Hello and welcome to my talk. My name is Arjan Berger from the University of Toulouse, and I will talk about Clifford boundary conditions for the study of periodic Coulomb systems. So first I give a brief motivation of this work. So we are interested in describing periodic systems that have an explicit two-body Coulomb interaction in the Hamiltonian. And this could be important, for example, to describe strong correlation, because we know that methods such as DFT that use an effective potential are not very good at describing strongly correlated systems. So the methods I'm thinking of are configuration interaction, coupled cluster theory, and these kind of approaches. Now, when we have a Coulomb interaction explicitly in the Hamiltonian, we are going beyond the one-particle picture. But this means that we can no longer use the standard Born-von Karman periodic boundary conditions because they apply to single particle wave functions. It is of course convenient to use periodic boundary conditions, and therefore we have to come up with an alternative approach. So we recently proposed to use so-called Clifford periodic boundary conditions together with a renormalized distance. So our approach can be summarized in the following 4 steps. So in the first step, we isolate a fragment or supercell out of the system. So for example, in the 2D case, we could take out this square. And then in the second step, we join the opposite sides, so A with A and B with B. This would create a regular torus. If you take a piece of paper and you do this, you get a regular torus. Now this is not very convenient to implement in practice, this geometry, because a regular torus is curved. Therefore, instead of a regular torus, what we do is we modify the topology of our supercell to that of a Clifford torus or square torus, because by construction, a Clifford torus is defined to be flat everywhere. Now, the third step is to define the distance that we need to use inside the Coulomb potential. So we choose to use the Euclidean distance of the embedding space of the Clifford torus. Now, it is difficult to give an illustration of a Clifford torus. It's impossible. Therefore, I show you what this Euclidean distance in the embedding space would look like for a regular torus, which is given here by this dotted red line. So you see that it is indeed in the space that is surrounding the torus and it does not lie on the surface of the torus. And the final step of our approach is to converge the result with respect to the size of the supercell. Now, in the remainder of this talk, I will give some applications of our Clifford approach. So the first application is a classical problem, namely the calculation of Madelung constants of ionic solids. And here we can apply our Clifford approach, and we can show that it yields a simple direct sum solution of the problem, as opposed to the more complicated Ewald type solutions. So here again is an illustration of a regular torus, because it's impossible to give the same illustration for a Clifford torus. In this case, of a 2D sodium chloride crystal on a 2 torus. So now I will show you some results for the 3D cesium chloride crystal. So in the last column, we have the Madelung constants calculating for Clifford supercells with a certain number of ions inside. So that is given by the first column. So K is the number of ions per side of the Clifford supercell. And we see that we quite rapidly and monotonically converge to the reference value listed here below. And this is opposed to other direct sum approaches, which are the other 2 columns. So for example, if you use Evian's approach, we do not converge to the reference value. It converges to 2 different values, depending on whether K is odd or even. The details of our approach can be found in this reference listed here below. We also used the approach to calculate the ground state energies of Wigner crystals. So Wigner crystals are crystals made up of electrons. So it was predicted by Wigner about a century ago that in a uniform electron gas, when the density is low enough, the electrons will localize at crystal lattice sites. And so here we calculate the ground state energy of a Wigner crystal, of Wigner crystals, that can be expanded using this asymptotic expansion. So the first term corresponds basically to the Madelung constant. It's the energy of a classical Wigner crystal. And the second term corresponds to the 0-point correction in the harmonic approximation. And then the other terms are anharmonic corrections. Again, a small illustration. So in the 2D case, the Wigner crystal is predicted to be to have a triangular lattice. So here is the triangular lattice on a regular crystal. In our calculation, of course, we use on a regular torus. In our calculation, of course, we use a Clifford torus. So here are the results. So we can efficiently do these calculations, so we can get very accurate results, several digits for eta 0 and eta 1 in 1D, 2D, and 3D. And all the details can be found here in the reference that is given here below. So far I've given you some applications, some classical applications and semi-classical. So we have also, we're also looking into the quantum problem. So this is the work, the thesis work of Miguel Escobar Azor. So he's been looking at Wigner localization at low density of few electron systems of so-called Wigner molecules using our Clifford approach. So here I will just show you the results for 2 electrons, as I think it will explain the idea. So when we have the full quantum problem, we of course have to describe the wave function. So we need a basis set. So here we use a Gaussian basis set because we want to describe localization of the electrons. And what we do is we use a regular grid of Gaussians to be sure that we can describe the wave function in the whole of the Clifford supercell. So here on the right is an illustration of what this looks like in the 1D case. We see that we have equidistant Gaussian functions. Then we create symmetry adapted orbitals out of the Gaussian basis, symmetry adapted to the translational symmetry. From that, we calculate the 1 and 2 electron integrals. So in this symmetry adapted basis. And finally, in this case, we can use exact diagonalization because we have few electrons. The details can be found in the references listed below. So in this, we can accurately describe the Wigner localization. So here I give you an example of the 2D case. So 2 electrons in the 2D Clifford supercell. For two different sizes, so L is the length of a side of the Clifford supercell. So on the left, it's equal to 10,000 Bohr, and on the right to 1 million. And I show the 2-body reduced density matrix, where we have where 1 electron is fixed at the origin at the 0,0 position, and then we study where the other electron will localize. And as expected, it localizes in the middle of the square because that's the furthest distance from the origin. And we also see that by increasing the length and thereby reducing the average density, the localization gets stronger. The 2-body reduced density matrix gets more peaked. Details can be found again in this reference below. So finally, I wanted to discuss a related problem, which is the definition of a periodic position operator. And this is related to the fact that we have also been looking at another way to characterize the Wigner localization. So one way was the 2-body reduced density matrix, but you can also look at the total position spread tensor of the electrons. So it is defined here by this expression. So basically, it is the variance of the many-body wave function. So whenever the variance is large, it means that the system is delocalized. When the variance is small, it is delocalized. This total position spread, TPS per electron, so when we divide lambda by n, the number of electrons, is also known as the localization tensor. But as you see, for that, we need to have a definition of the position operator that is compatible with periodic boundary conditions, because we're working in periodic boundary conditions. And the standard definition of the position is incompatible with periodic boundary conditions. So the question we were asking ourselves is, can we define a 1-body position operator that is consistent with periodic boundary condition? Well, And the answer is yes, but there's actually only one possibility if we impose some reasonable physical constraints. And the periodic position operator we found is given. So in 1D, I just give you the 1D expression. The 3D expression can be found in these other papers listed below. So we have a complex position operator, and it corresponds, let's say, the distance of this, the distance corresponding to this position is exactly the Euclidean distance in the embedding space of the Clifford supercell that I introduced in the beginning of this talk. So this position operator is related to this distance that I defined in the beginning. Okay, I come to the end of my talk. I would like to thank my collaborators, and in particular Stefano Evangelisti, with whom I did all of this work, and of course some funding. Finally, the conclusions and a brief outlook. So in conclusion, we have, I hope I've shown you that we can use this Clifford approach to efficiently describe periodic Coulomb systems. As an outlook, we are now looking at the quantum treatment for more than 2 electrons. We've made good progress there. And of course, we would like also to extend the approach to indeed configuration interaction and coupled cluster theory. Finally, if you have questions, don't hesitate to email me for any questions that you might have. Thank you very much.